Hello everyone, I'm Sai Kishore. I work as a senior robotics engineer at PAL Robotics in Spain. I would like to present a roster control, a versatile real-time control framework. Unfortunately, I have to do this remotely, but I'll be there tomorrow. If you have any questions after the presentation, please feel free to find me. I'll be very happy to address them. So after the presentation, you should be able to understand why ROS control, when to use it and when not to use it, and how it can help you build your applications and build your robots and your control ecosystem. We are the maintainers of ROS controls repositories: Bense, Dennis, Christoph, Mark and myself. ROS control is a framework that allows you to talk to your hardware in a real-time way, as well as it provides you a nice hardware abstraction layer, and you have a nice control schemas to reutilize the controllers and reutilize the control schemas with the different control architectures, like how Nav2 is used for the navigation and Movie2 is used for the motion planning. ROS control is mainly for having an abstraction layer that's similar for the simulations as well as your real robot. I would say it's pretty much similar to how Orocos has been with the robotics in the past decade. ROS control was inspired from the PR2 control manager, which was developed for controlling the PR2, and we at PAL we tried to make it robot agnostic, and it was adopted by many robots at that point of time. And ROS control, we started with the idea to implement the most of the features of ROS control, but more agnostic and more modular way, I would say. And if you see till date, it has gained a lot of I would say like a craze, because many robots have adopted it, including the humanoids as well as the mobile bases, and some people are using it also to lift pegs in the wild. As I've said, ROS control gives you a layer of hardware abstraction, and that's common between different hardwares. Let's say you're building a nice application that sends a command velocity, and if you have a differential drive base, or if you have an omni drive base, that gets managed under the hood. And it also provides this nice abstraction that's similar to the hardware as well as to the simulation layer. Let's say here you have a nice application, you want the robot to navigate to the kitchen, grasp something and get back to you. So you send a navigation goal, that sends the command velocity to the base controller, that converts into the wheel commands. And the same likewise, like when you go with the move it, you plan the scene, you send the trajectory to the joint trajectory controller, or in this case arm controller, and it sends as a joint commands to the joints. And here, as you see, we also have a simulation hardware interface, which is a nice digital twin of the real hardware, and the interfaces are pretty much similar, so you can pretty much mimic what the robot does in the simulation. And this is nice because from the architectural point of view, you are reducing the sim to sim gap. This is the whole workflow of the whole ROS control ecosystem. So I'll be explaining you in different blocks, like hardware, resource manager, a control manager, and the controllers, so you get a bit of idea of what's happening under the hood. Hardware components. This is where the real communication with your hardware happens, and it gives you a nice abstraction layer, so you can plug in multiple hardwares or multiple sensors into your robot ecosystem. And we have a resource manager which is responsible for loading these hardware components. We have mainly three hardware components. We have sensor, which is mainly the reading. We have IMU sensors, force-talk sensors, which basically you read the sensor information, but you are not able to write to these sensors, right? And on the other hand, we have systems and actuators. System is basically like you can control the whole robotic arm, and actuator is when you would like to control only one actuator. So basically the difference here with the sensor is with the system and actuator, you both read and you're writing as well. You're reading the actuator information, let's say your joint encoders, and you're commanding the joint with the position control, velocity control, or torque control, etc. The interfaces can be configured at runtime, so it's pretty much robust. Resource manager. This is who is responsible for loading your hardware components into into the ROS controllers ecosystem, and it imports the state interfaces and the command interfaces. What are state interfaces? This is basically where you are allowed to read information, but you're not allowed to write. And command interfaces is something that you are able to read and write. So state interfaces is used mostly for the proprioceptive sensors and the external sensors, and the command interfaces are mainly used to command your hardware. Control manager. This is the main entry point for the ROS users, I would say, because this is the one that allows the users to load the different control strategies and swap between the control strategies at runtime, as well as this gives you a nice abstraction layer that to establish the communication between the controllers and the hardware. And it gives you a bunch of services to load the controllers, configure them, activate them, deactivate them, and unload them. The control manager has two different threads, real-time and non-real-time thread. In the real-time thread, we have three different functionalities. One is read. Here, we read the data from the hardware and then update the state interfaces. And then we also handle the hardware errors in this method, I would say. And then we have update, where you run the update cycle of the controllers. And we also maintain the controller update rate when we have a different update rate. And we also maintain the controller switching, so it happens in real time. And depend if your controller is failing, we can do a different strategies that I'll be explaining you later. And write is basically like once your controllers have done their update cycle, so they come up with the commands that you would like to communicate with the hardware, and this is where it happens. And here also the hardware errors, write errors are handled. So this is the main simple diagram for the beginners. As I mentioned, control manager has two loops. One is real-time loop and the non-real-time loop. In real-time loop is where you read the sensors, you update the interfaces, and then you update the controller, and then you write the hardware. And the non-real-time loop is where you receive the commands. Let's say that you're sending a trajectory and you're sending some PID parameters, or you're sending the trajectory commands or the joint commands or your command velocity of the base. Everything is received in the non-real-time loop, and then it is shared with the real-time loop with a thread safe way, and things happen under the hood. Roster controllers. As I said, it gives by loading the controller goes to unconfigured state, and then when you configure them, they go to inactive state. And when you switch the controller, you can toggle between inactive and active, and you're able to unload them in both in unconfigured and inactive state. What does roster controllers provide? So you can loan the command and state interfaces. Basically, let's say that you're loaning the sensors information like IMU sensors and the joint proprioceptive sensors, and you are also loaning to command the joints here. And let's say that my control manager is running at 1 kilohertz, but I would like my controller to run at 50 hertz. You can simply do that by setting a parameter, and you can run them asynchronously in a different real-time thread. Just because let's say that you have a controller that takes longer, let's say 2 seconds, but you don't want other cycles to block because you have to maintain the 1 kilohertz loop. So in that case, you can run them asynchronously by setting an update rate, and it works by simply setting a parameter called isAsync. Chaining with other controllers. So this is a very interesting concept that's new with the roster control. Basically, the idea is you build one controller, let's say the PID controller, and you can chain it with joint trajectory controller, which sends the joint commands, and then you do the PID loop, and then you send the current to your actuators. So the idea is to have a more modular way to plug in, plug out the controllers, and so the users will be able to reuse them. And fallback controllers, this is nice. This is the one I was telling earlier. If your controllers are failing, you can have a fallback controller strategy. Why did we implement it? Let's say you have a humanoid robot and it's walking, you have a walking controller that makes it walk, but suddenly it fails and the robot is gonna crash. But you don't want that to happen. Maybe you would like to crash, but maybe softly. You don't want to crash abruptly, right? So you can have a fallback controller. When your main controller fails, it falls back, the fallback controller activates, and then the robot is safe, might be able to safely land. And the roster controllers also have access to the joint limits. And we also provide a way to inspect each and every variable of the roster controllers. Let's say you have a variable foo and variable bar. At each and every update cycle, you can check the values of the variables so you can easily debug them. Semantic components is also a nice concept. Let's say that you have a IMU sensor where the whole, each and every component of it makes sense together. So that's when we call semantic components. So you can ask them by just a name and you get the information of all the semantics internally with it. Plus, it's nice because you have a bunch of controllers that are already open source and you can use them out of the box. You don't have to implement any logic by yourself. So here are some standard controllers that we provide. The PID controller and the forward command controller, which is basically you send a command that gets returned to the hardware directly. And we have a general purpose input output command controllers. And for the mobile robots, for the navigation, we have steering controller, omni-based controller, mechanism drive controller, and differential drive controller. And for the industrial arms, we have the joint trajectory controller, which also interpolates the trajectory for you out of the box. And we also have the admittance controller. And for the different grippers, we have some controllers and the broadcasters, the joint state broadcaster, which is one of the important, because you would like to have the TF working. So you need the joint state topic. And the joint state topic is published by the joint state broadcaster. It's basically reading the sensors of proprioceptive sensors of your hardware and put them into the joint state topic and publishes it. And the same for the force torque sensor, IMU sensor, and range sensors. And this is something cool that we have recently, the force torque sensor. You can plug in some filters into the by just configure them in the conf file, and you will have a filtered signal outputted from the broadcaster. And the community has, as I've mentioned, the community has adopted roster control widely, and here are some of the most widely available hardware drivers. You can see them in the link that I have pasted in the down. Hardware components. So let's say you have to write your own hardware component. What does the roster control offer you? We offer the data management in the hardware components. Let's say if you have a hardware roster control tag in your URDF, you mention all the command interfaces and the state interfaces. They are automatically created for you in the framework. And if your URDF is as close to your hardware, it's gonna work. And you can also choose to have read and write. Let's say you're plugging an industrial arm onto your mobile base, and your mobile base runs at 100 Hertz, but your industrial arm has to run at 1 kilohertz. And in that case, you can choose that only one part of the component needs to run at a certain frequency. And asynchronously as well, like this 100 Hertz, maybe it's taking longer, it's a blocking calls. You can also make sure that this is run asynchronously, not affecting this industrial arm. And we also handle the read and write callbacks by changing them to inactive state or active state accordingly. And we have the mock hardware plugins that we offer. This is nice because if you want to write a nice CI/CD test, you can use this mock hardware that does the integrations under the hood. So you have the join commands and everything. So it's pretty much reliable, I would say. And everything that we have in the hardware components is real time and thread safe. So for instance, we at PAL, we are running a hardware component at 2 kilohertz on our humanoid. And I have every time we see some performance issues, we do fix upstream. And likewise for controllers, you can also introspect the internal variables of the hardware. Plus, you get to know the statistics of read and write of your hardware component. Let's say your read is taking longer, or maybe your read is not periodically being called. This is something that is provided with the roster control. And you also have a bunch of open source hardware components, as I mentioned in the past. Asynchronous hardware component. In this diagram, if you see, we have a slow controller running at 100 Hz, and that's run in a separate loop. And this, likewise, in the base hardware interface, which is running at 50 Hz, which is blocking, these can also be run in a separate loop just by setting the is async property to true. And everything under the hood is configured to run asynchronously. Joint limit enforcement. Roster control internally enforces all the joint limits that you specify in the URDF. Let's say in the URDF you say my joint 1 cannot go more than 90 degrees. That's enforced from the architecture. But the only thing is, it's enabled from SASE on, but in SASE you have to enable it because it's disabled by default. The only limitation is right now the jerk is not limited, but we'll be coming up with pull request soon, so even the jerks are handled. So for the industrial arms like KUKA and Universal Robot, this is being used. Real-time improvements. We also provide a bunch of parameters, so you can make sure that the roster control runs on a specific core of your setup, and also you can set the thread priorities and asynchronous, and we use a monotonic clock so you don't have issues with the change of time in your hardware. And we also have scheduling policies. When you run things on asynchronously, you can choose that you would like the hardware to have its own clock, or you would like to synchronize with the controller manager. Diagnostics and introspection. This is nice because control manager provides you two different topics, which is the topic of introspection, where all the variables that you are introspecting in the controllers and the hardware will be published. You can plot them using the plot juggler, and it works. And likewise for the statistics, you can read the execution time of each and every controller, read time of each and every hardware, write time of each and every hardware, and the whole cycle time of your whole control manager. And it is also being published in the diagnostics topic. Control manager activity topic, it's nice if you want to make some nice graphical user interfaces. Basically, it gives you the life cycle state of all the hardwares that are present, and also the controllers that are actively controlling. So this is we have a project charter. If you're interested to know about the ROS controls project, please take a look. Please scan the QR code. We do bi-weekly meetings. We do a meeting every 2 weeks on Wednesdays at 7 p.m. Central European time. If you would like to join, please scan the QR code. And we have a repositories under the ROS Controls GitHub organization, and we have a bunch of documentation in the control.ros.org. So if you have any questions, if something is not clear, feel free to open issues. We will be happy to correct them. So I think the next one is going to be on 31st December at 7 p.m. Central European time. If you would like to join, feel free. And if you would like to contribute to the ROS Controls project, you don't have to only contribute by making up the code, but you can also review the existing pull requests. So if you have some free time, please do so. For the beginners, like if you would like to understand how the roster control works, and if you like to have some demos, we have around 17 demos in the roster control demos repository. So please take a look. It is, if I'm not wrong, it is from basics to also advanced use cases. So it's pretty interesting. Like if something that's not clear to you, open an issue. We'll be happy to add an example, or we will be directing you how to do it. The thing with the roster control is we don't offer ABI stability. So every time you have a sync, we recommend you to rebuild your code. It's just because for us, and from the architectural point of view, if you have any issues, we don't want the robots to suffer. Maybe there is some safety concerns. So that's the reason that we might break ABI, but we're trying to come up with some approaches to reduce the ABI breakages in future. And if you need some feature that is in the recent versions, remember that you can compile the rolling version on older versions of ROS distros. Like let's say you want to compile the whole rolling stack, you can compile them in Humble, Zazie, and Kilted. They are supported right now, and we have a CI to ensure that. I know that India loves us. We have around 18k visits this year from India, and most of them from Karnataka, Maharashtra, and Tamil Nadu. Thank you so much. I hope that our documentation is helping you a lot. Please, if something is not clear to you or something is not helping, please open issues. We'll be happy to address them. Thank you for being here. And I should thank Be Roboticized, AIT, Locus, PAL, and Picnic for dedicating some of their resources to develop the ROS controls architecture for the community. And I hope you enjoyed the presentation. If you have any questions, feel free to find me tomorrow. I'll be very happy to address them. Have a great day at ROSCon India. Thank you.